Okay, so I did some compilation here of the application console. This is update to the Planar Transformer software, and I did a standalone with embedded runtime in the exe. We have this for Windows, Linux, and Mac, ARM, Linux, and this one is Silicon Mac, and this one is Intel Mac. So we have all the platform covered. So let us run it and see what it looks like. I'm going to do a simulation. Right, and this is what the splat screen look like. Planar Transformer, a PlanarXpert, that's the name of it, and my company name, Encotech Electronic Engineering and Technology. I don't know, this splat screen, I might change it, I don't know. But I have a lot more work to do. I have like report, exportation, to export in different formats, and measurements. So measurement is important, right? All that would be in report. Okay, so this is it here. I have reset for results, reset meshes, build the geometry, predefine mesh, user mesh, run the compute the mathematics, compute the loss, which losses be like this. I have to buy reset for the loss. So every time I look at things, is one or two things I have to do. So this is old data. So let us I already have the default as this, right? So I will just pull things to the corner a bit. Right, so we have like, this is the geometry here. If we change the geometry and we put like the 7 here, we will see difference over here when we build. You're gonna get wider, one of the legs, well, all n legs. Right, so this is what it is, but we're not going to be using that because that's not a real transformer. So we just build back. Right, so let's move on from there. So we have like the complete geometry, we have the core geometry, we have the configuration. If we want to put air gap, let's say 100, or let's put 1 millimeter, right? So we build that and we will see a space air gap, but we're not going to use any air gap. But that's showing another feature, right? So this is what we have here, air gap. So we're not going to use any air gap, so we leave it alone. And when it comes to the magnetic path, effective magnetic path length, this is as A is actually with the foilers around here. This is part A, and if we use part B is a foil in the outer leg and another foil in the outer leg. So you know, if we want to do it that way, we could do it that way, right? So it computed, right, for both configuration. When I have like all the other cases to build, I'm working on this one to make sure I get everything right, I have to do, this is 2E core, I have to do one more to I core, which will be an option after adding to this, right? Everything is there, just I write in the software part of this now. And these are the foil specifications. This is, we could put this to be 75, 75, right? And 75, 75. So the primary and the secondary, we're going to make here a little more curve, and we're going to make this side here a little more curve. So we could build that, and we will see the effects of here, and here we'll get curve. Right, so that's it there. So the entire transformer will be curved like that. Great. And we had the turns and the layers, right? So all these things was put. This is simulation model. So when we build and we can make decision and build and how we want to build it once we had the specification of thickness and the amount of turns, you know, things like that, and the amount of layers, right? How you want to build it by configuration and mechanical engineering, you know, that is something you put into thought. And these are the core material itself. You get all these things from the data sheet as well. You know, so it have more details that I put equations to, right? I may put a something like a part number here to indicate the core part number, so you know when we do the report will have the actual part number for this configuration, which is important. So you know when we come and we save as or save, you know we could have the entire simulation, but if you wanted to create a report, and you know simulation take up space when you simulate, so you know we might not have space for everything, but we could save the report files and we have everything we could just punch in and run into the simulation. So that's that. And now we're going to do the meshing. Now we have like the corners here to mesh. You know you could use this, you can enable this, and I will put this to put extreme here, and we just mesh. We mesh in with this enable, right? So we see the edges over here have more meshing to get more details. You could do that, or if you want to, you know, just simulate just to get the average, we could just uncheck this, so we'd have to go through, you know, multiple computation. Okay, so this is the meshing here, right? As we can see, the corners itself, so it take more computation to you know calculate this, and you know take more time, but the end results will be more precise, right? But if you don't want to be doing heavy calculation and you just want an average, the averages work good, it doesn't be far off the precision, right? So if we uncheck this and we go back and we compute the meshing, we will see it will be regular like this here, all to the edges here. Okay, so this is what it look like now. So you don't see no fine details in the edge. So I will put this to be about here, so, and I will mesh this a little more finer, but you know at least it wouldn't be that bad like this. But you know this will be fast to simulate, just to give you an average. So let us mesh this. I put this one instead, sorry about that, is this guy here. you can see the progress bar moving, a little more faster than the next one. I had to pause the others because it take a while to mesh. Okay, so this is this one now. So we will run the simulation for this. I thinking about putting it to pause, but before we do that, so we'll work with this. We just minimize this. And let us go to the other options here. So we have simulation settings here, and simulation settings, we could do sample, the minimum sample. We could do less than this, but it wouldn't be recommended to do less than 10 sample, right? So we run 10 samples, and the pulse width sample itself here too as well, 10, right? So we have the period sample, which is, we'll look at it this way. So let us draw, this is a wave here, right? This is the period, well, starting from here really, right? So our period is these guys here, right? So this is where we say we use period 10 samples, right? 10, so it'll be like 1 2 3 4 5 6 7 8 9 10, right? So we have 10 samples here, and then we had the pulse width, which is basically this guy here, and we do 10 samples inside here, right? So this is basically what we're referring to. And the simulation time, right, this is a runtime here, will be, this will calculate these guys here. So if I put 100, you will see a difference in time, the stop time here. So I move this here, and let us put 100 here, and we will see a difference here in the step time. So 105.7 nanoseconds, which is 0.1057, right? And we go see, like if we having any issues with over ringing and high frequency ringing, we will like to see those information. So that depend on how much steps you do with the pulse width, which you will see it, we covering those fine data. So just for faster simulation, I will just put the minimum. So we have the planar transformer input that we switch any transformer with. So I switch them at 47.3 kilohertz, the primary, which will be 18 volts, and the current here, you want how much amps is self-determined there, but this option currently is not active on this. So I will put an button over here when I continue to resume to work on it. This is a test, and when I put a button now, it depends on voltage or current, right? Now the voltage with the calculated ohmage will determine the current, right? And also the load. And also if we choose the option to put current in, then we will determine the voltage according to the ohmage to achieve that current. So that is something, right? So the secondary resistive load itself, let me just kind of put this guy here. So we have a diagram here, right? So we had these switching MOSFETs on them here, and this transformer. So across the side, the secondary side, we will have this resistive load over here, right? I didn't bother to draw like the amplifiers and whatnot, but we just say we have a load of 1 ohms, right? Now there's a vacuum enclosure that this need to simulate in. I do not want it to be over large or over small, so pretty much I have like a percentage ratio here, right? This more like a ratio to the size of the box. So if we put this ratio, the box itself is invisible, but it actually um, when you're doing your geometry for your transformer and your foil, the box actually grow or shrink according to the size. So your planar transformer size govern the box with a ratio that we give it here. If we give it 1, it will be snug on the top and the bottom, the side and inside, and the front and the back. It will be there, which is not a good idea, right, for simulation. But for whatever reason, if you have a aluminum box or something, or a copper box that you want to put shield this thing to the very small for whatever reason, compact I guess, then you will need to simulate in that type of environment. So you put one, you just remove this 1.25 and let's put it 1, and you have it pretty much that. So that is like 1-to-1 ratio, so you can work out this in that sense, right? We have the component. I need to remove a P over here, right? I've been working on this about 8 months I think. 8 months, and not just only this software, I had a next software in front of this, which does calculation not for 3D but as 1D and dimensionless and made huge. So pretty much the information from there will be coming in here. So yeah, because when you actually specify the geometry of the transformer here and the foil, you will have to simulate, which could take very very long according to the resolution you want to simulate with, and you don't want to be computing something that you're not certain about. So I develop a software for that to give you the best results you can get before you go and do a long simulation. And that next software, it instantly work right away, like seconds right away. So that's do all the configuration that you want to do. It have like the complete load, amplifier, everything. And once we get those information and put it over here, we have our next calculator I will show you just now. So the component YZ axis, right, as enclosure, right, and we gain the value of the size of the enclosure box itself. So if we know we have a certain length, right, I have to put in some information and whatnot for the foil length, the total foil length. I have to put that out somewhere. Now this planar loss calculation is for the heat. I have to reset this. I have to put a reset button over here for that, right? I didn't put that. I overlooked that, but I will put that to reset and default this. This is all later, right? So if you're on a certain simulation for a certain period, we see we have a stop time of 111, right? I will do some code to pretty much not allow it to cross this time. So the time that you could put, I guess that I will leave this box and I will put a slider itself, and whatever time we have available we get just put it in max here, and we just run a simulation time minimum. I'm not sure if I could do 0 seconds, but I will figure it out in the sense I'll test that code. So we can slide the box across and whatnot, and even if we want to punch in this manually, and if you cross this, it will just prompt you and tell you please enter a number less than this. So I have to write that code in for that, right? So as I say, there are a lot of things to do as yet, but 90% of this done. I have to do case 2, case 3, case 4, case 5. Case 2 is a repeat of this, so that should be a breeze. Case 3 will be inductor, right? We'll be doing the inductor 2 as well, the filter inductor. Case 4 is a duplicate of in case 3 inductor. And the reason why I had two cases is that when we run a simulation and we look at the data, we study it, we understand it, and we want to tweak on it, we leave this case here and we go across in this case and we enter something that we believe will work better, new parameters that work better, and we can have a comparison itself. Now if we come across to case 2 and case 2 want to know to be better, then we understand case 2 data and we go across to case 1 and try something else. So we kind of climb in the ladder that way, right? But if case 2 is terrible, then we can point to your next data, or we could just stay to case 1, right? So it depends on your time and your patience and what data you're looking at and the accuracy of it. So same thing you do with the inductors itself. Case 5 is the inductor, filter inductor with a filter capacitor, and pretty much case 5 will be, right, we have the battery here, right? We say 18 volts, right? VDC, we have 18 volts. We have the inductor, we had a low pass capacitor for EMI interference, right? And we have, right, this is the MOSFET itself here. I just join a switch for now. I'm going to draw the entire topology of the H bridge, right, which this could be kind of most like a resistance here when it close, and this is the transformer. I'm not going to do the full entire H bridge. This is a straightforward concept to show you what's going on, right? And this is our resistive load, right, our 1 ohms load, which is this guy here. Now the best inductor case we could choose for this, we could choose the best transformer case for this, and this entire simulation is case 5. So case 5 will be, you know, in this be case 5, right? So case 5, this case here, case 5 will be this entire thing here. Now we have to take into a consideration that while we're doing this, right, I would like to know, before we get to reach to that case, if we have case 1 and case 2 data, we would like to compare case 1 and case 2 data, right, in the sense that if we could have a percentage between them, right? So we have all the, you go to this one here, we have all these readings here, all these measurements. We would like to have case 1 and case 2 measurements of this be compared. So what we would do, I will have a comparison tab. So when we run both of them, and once both of them pretty much enable, comparison tab will be active. So when comparison tab active, we know we ran 2, and we could pretty much look at what the comparison is, so we know which one is better according to certain areas, which is better, so we can make better decision in the comparison before we gonna run back case 1 or case 2. So once we do that, I will have to put a simulation time when the simulation stop. And the reason why I have to put simulation stop, because if we take a break or the amount of work we probably doing, we would like to know which one of the simulation last was run, which is very important. We don't want to actually look at the data at that time, right? Because whether it be good or bad, we need to know what our ideas and decisions were, so that will be the last one that ran. We will have the time stamp on that. So once we have the time stamp on that, we look at the case itself, we know exactly which one we're making the decision for versus to the next one. right? So that is important. Case 5 is the final simulation based on the decisions that was made to make the best simulation out of the 4 cases here. So case 5 is just only one case to run, and that's it, right? It's just to put the two components together, inductor and transformer together. So that is the only reason why it is that we will do case 5 once, but these guys are important. So that's that. Now let us look at this option over here now, right? So this option over here, the magnetic density results, we have graphic 1, 2 and 3. We have like 1, 2 and 3, right? And 1, 2 and 3 basically is where we can measure information, but we have nothing, no data available, right? This is a blank, no data available here, right? This one too as well, we have no data available, so we have nothing here. But this one have data from the old one, so we will get different data here. So this is the heat loss self. What's meter third, right? So when we pretty much get data, we can actually look at the data at different region and see if there's any issues and whatnot before we make a decision to save it, use it, things like that, or to run back. So we could do our check here, and pretty much, well, when we run simulation, we will see the other results itself, right? This main one here, the main graphics, is, well, let's lock here, right? The main graphic will do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 switches across. This one is fixer MOSFET power loss and resistive load power, right? So these two is fixed. This is fixed, this is fixed, and this is fixed. This one you can navigate across the rest. So you can do the measurements inside here, just only these three itself. I was going to do that, but I don't want to confuse the workflow, which is these three is fine, and this is just a browse through and look at things, right? So that's that, and we just minimize that. We'll look at this. So now when we look at this here, the data sheet for this MOSFET is 750 micro ohms, which is an ultra low MOSFET. It's a new model MOSFET, probably about a year old release. I use it two in parallel to each other, and this is a MOSFET group in parallel. This is another group here, this is one group here, and this one group here, and these is like a kind of complementary, right? Negative and positive swing, right? Same thing, negative and positive swing, and we have them in an 8-bit configuration. Once we determine these two here, we determine the rest basically, right? So if we put 3 here, that means we need to use 3 here, 3 here, 3 here, and 3 here, right? So when we actually increase the MOSFETs, we increase costs, but we decrease the ohmage and losses, right? But the thing about it is that we increase capacitance to the gate. So we had to take into account all these different areas. We just lose energy in the drain to source capacitance and the diode region itself. So it's important. We have to look at every losses. Like faster switching is more losses, depends on the components that we're using for switching. Now the other software that I pretty much been using, this was PlanarXpert, this one here. Right. So this is the software here that I will be using for determining. Before we go to the next application, this is the first software that I was designing. This complete, And if we looking at whatever power that we want to use, we could pretty much scroll here. We could say, okay, we want to have 4000 watts. We hit enter. So um, if you want to have a minimum of 4500 watts, we hit that here. If you want to have a maximum of 11, let's say, actually no, you can't really type in anything over here, right? So this, if we determine here is 5500 watts, right, minimum, it will automatically calculate the peak. So the peak will calculate here. How I wrote the calculator, I don't remember that. So yeah, so it will give you the peak. So you could go from here to here, and I do it like that because you like to do your calculation within these areas. Now we have like, if we come around here, it will give we the power max here, and we gain the RMS, we gain the peak. So depends on wherever watts we want to have, whatever watts we want to have, we could pretty much get that. Now we could choose for the calculation. This is transformer here. We say 18 volts. We could scroll this guy towards that, right? We say 18 volts, right? My bad. Over here, 18 volts, right? So 18 volts is kind of lock over there. This one over here is a kind of self-calculation business. When we put this in and we scroll in these guys here, right, it kind of like automatically calculates here for us, right? So if we this is 7000 watts, right? So 19 volts, yeah, give or take, right? So this is transformer here. We need 114 volts over here. The voltage drop will be 113 volts, 0.6, and we have, so this here secondary MFS, right? So the secondary side is that we have 716 amps here, right? So this is the primary, this is secondary, right? We look at here, we have 1 ohms here, we have people 47.3, right? Put that here. We could choose the RMS values if we want to put here too, or you could choose the peak, right? So it depends on your calculation what you're looking to do yourself. You have these options, and we could double click inside here, and this will come up. We pretty much stop this guy here. We have to stop this in order for this to actually receive data from here, right? So you stop, whatever data was over here, it will come across here. Okay, it probably finished compute. Okay, it's still computing. It's take a while to settle in the amount of coding that I had to do, right? And we had what, 7000 watts we did choose, right? So 7000 watts finally come. We have 48%, right? So that is fine. The duty cycle, and we could look at, we have a pre-configuration here, which we have 1 2 3 4 6. If you want to put 12, up to you. You could put 12 ohms there, put 9 ohms here, but you have to put this to run first, right? So you can see the effect. If we put 8 ohms, right, we put 12 ohms, right? So okay, so we have so we could put any ohmage over here configuration, and these expression over here will give we the RMS, the peak, that for the current, the power, the voltage, and the peak here. We will see these guys here. So whatever change we want to make, the one in yellow is what will be going back here, right? So if we say we want to have 2 ohms, now we put 2 ohms here. What we had over here was 1 ohms before. So when we click, like, stop, right, it offloading the value for 2 ohms there, right? So everybody going all crazy around here, right? So start back this here. Oh, my bad. When we end that, we have to turn off that, right? Oh, my bad. It then came across, right? Put 2 ohms here, right? Right. So let's try back that here. They put 1 ohms here now. Okay, yes. Run this as 1 ohms, right? Right, now the 1 ohms went across over here, right? So that is fine. So 1 ohms come across here and update from 2 ohms. So we find this. So whenever we make adjustments here, we come across here, right? And we just run back the app, and we calculating, okay, if we have capacitors itself, if we have, like, building a base amplifier, and the base amplifier now, say 12,000 watts, 7,000 watts, and then we could use synchronous rectifiers. So if you're using synchronous rectifiers or diodes, depends on what you want to do, right? I had a calculation here for that. So what we be looking at here, we need to have the efficiency of the capacitors to be this, or close to 100. Most amplifier does not give you the real thing, right? And 20 hertz, this is how much joules we require at this power rating. We have 7,000 watts, right? So we have 13,000 watts in capacitance, so we could come down with the value. Go up here a bit. Sixteen capacitors, 7,000 watts. Okay, say 16 capacitors, right? 16 capacitors, right? So the total capacitor discharge is this amount of energy. We using that. The time frame of discharge, 20 hertz. So if we put this now, we can see how much discharge I have here. So if we want to do something like 20 hertz base, right? At this capacitor rating, we get 7,400. So we could pretty much see we matching this guy up here, and this is 12,000 watts audio power level, right? So we have the match, right? Although they're saying the efficiency of the capacitor is not efficient enough, the total wattage, so you have to, if you want to match, but this is your minimum, and if you want to match, you will have to go, 100% or whatever the case might be, and you end up with 13,000 watts of energy that you have. But it's all about matching here, right? This is the power level for the base, right, that we need at this ohmage, 1 ohms. So we will see the losses and everything here. Now when you have a amplifier, we would like to have power bars, because the PCB board will not be able to support any copper the PCB board will not be able to support the current, so we need to have PCB bars. So if we have the length, height, and width, we could determine this is the skin depth here. We could determine everything in blue here. So the skin depth, right, and all the other configuration here. So we can enter the length, the height, and the width, and we determine all other values and these guys. 47.3, right, and we will get the correct information. So you have to punch in your frequency over here, right? So that is that one. Right, stop. And if we had the width and the length, itself over here now, punch in 47.3, right? Always in like 2 and 200 and stuff, and then I kind of like literally put those as a sample but different values so it won't look fixed itself, so you pay more attention to it. You change it according to over here. I didn't bother to transfer this across here. I say, you know, this could be a standalone too. So it depends on your current density you want to use over here, right? You pretty much could do that. So whatever current density that you want to do, I have some standard current density here, 3, 4, 5, 6, right? You could go up to 8 and things, but you know, I just put some defaults here. So if you put 8 here and hit enter, you will get the 8 still, but when you scroll it with the standard, so either way you want to work with it, right? And if you do have the length and the height, length and height is basically this guy here, and we'll get the width. So make sure that whoever we want to find we could get, right? Now this is something that you could transfer DC across, which this would be irrelevant, right? You transfer DC across, that'd be fine, but when it comes to skin effect, right, when you change this here, you will see skin effect determine the height, right, which is really the thickness. So if we have 47.3, right, so what you don't want to do, you don't want to cross this, but when you look at the current rate and you have over here now, you say, okay, we have a certain amount of current, but we need probably 700 amps. Multiply this, or no, well, divide 700 by this, and we know how much strips like this we need. That is when we have to transfer switching energy from the MOSFET to the transformer. You don't want to put one thick bar. The current will travel in the surface, the internal will form heat, current will be pretty much a disaster. So you know, high frequency go, the current tends to travel on its surface, so you don't want to have a thick current bar, because you know that is for DC. DC is fine, but when you're doing AC, you need to run one or two of these guys itself, so you have to take that into account, right? I didn't bother to put these things here. If you're designing, you're supposed to know those things, right? And this is voltage going to the amplifier, and the amplifier with the load over here. So we're seeing 12,000 watts, right? Go RMS, right? We see 6,400 and something watts, right? So this is RMS and peak, right? So when you're looking at these guys, you'll see the power rating here. And so as I say, you know, what you want, wherever you're going to design, you know the energy that you're working with for peak. So that is that. I try not to stay in this, I try to go back to the next one. And current density here, we're designing for, well, you see I have 8 over here, and like the next one I didn't put that, right? So if you're designing for certain current density, 3, 2, right? So they say 3, and we pretty much will have to put in the geometry over here, like how we have the software here. Before I design the 3D simulation software. This was the first software design, and the data is pretty much to compute all our components that will work with a certain transformer core, certain material, certain dimension, and all these different things, right? And we had the current part here. We could determine that here, right? E and I core configuration to E core itself, right? So we had two configuration, either like 2E back to back, or this I coming on top here, right? I have to build that in the next one, which is a minor thing already there. There's already some codes and do that, but that is secondary matters, right? So equals part, this part, and okay, this is part B here I was talking about before. So we pretty much have these secondary turn here will be determined by power rating and all these things, and whatever voltage that is required that was pre-calculated. The primary and secondary will be calculated accordingly, right? So this will be like that. Now a BH curve. Now you go to the data sheet, and if you need to get information that you need to get for entering in these guys here, which will be where we put in information. Okay, right. So if we need to get the middle Tesla for the E core or I core here, we could pretty much open up this. I didn't design the software, this person designed that. I just call the software from my software, right? How to do I installer for the software itself with this to install things in certain locations. So so you open up the data sheet, open it here with the BH curve, and you measure. You have to measure. You get the data, and you punch it in over here. If you're looking at certain data itself, and when you punch in those data itself, we also have, right, where is this? Right, so over here now, when we actually have this information we gain from the data sheet, right, you notice the what is here will change. So when you punch in this here and have this over here, you'll be doing these other calculations itself. And over here now we could change the scaling, because some data sheets give you a millihenry, some give you a nanohenry, right? So whatever it is you're choosing, you're putting for the I core, the E core itself, how much cores you want. This core is just one core, right? So if you want to have a pair and make it longer for high voltage transformer, it pretty much going to be multiple cores. So I could do these things here, and when I put more cores, it automatically do the calculation and thing for part itself. Same thing I did in this other software. So this software guided by everything I have over here. I was just going to punch in things, and it's like okay, but then when I'm thinking about doing a report on this, it's like you have to have this in reference. So I like, what, I need to repeat this entire software equation. Is over 300 equation that develop in the background for this, right? So I had to do this back day too as well. It was painstakingly long, as I say, 8 months, right? And once we punch in those information itself, we put in all this data inside here, and it will calculate what is the permeability and all those different things, right? And we have the foil thickness and all these different nitty-gritties here. We'll calculate all this information, right? Everything in blue and purple and red is information calculated. Anything that in green and black, or black background and green, is inputs, right? And yellow, right? No, sorry, everything in yellow is inputs, Everything in any other colors is just results and monitors like that, right? So we have like all the calculation that we will find here, which is important when you run simulation in CTS, ANSYS, COMSOL. You will get these information, but this information is much more accurate because all platform, they give you the close proximity to it, but I pretty much gained some information and the others and I was not gained, so I end up had to build my own software because I need more data. So so we have like air gaps and all the different values itself. So if we have air gaps, they have calculation for air gaps somewhere around here. So once we insert any air gaps inside here, which is um where my air gaps calculation, the foil, I think that probably have to be somewhere. Air gaps, so we have air gaps here. So the air gaps, if I put air gaps will actually change values in a couple places, right? And we have all these different values for that. We see the efficiency itself, CTS, right? If I don't have a module design CTS, right? So CTS are console were developed on, you can punch in console or CTS value here, and this calculator and going to give you the coefficiency of the other simulator and this, and we are getting RMS power efficiency input. We are getting actual efficiency 90%, things like that. If things matching up with this and the other platform, when we punch in the other platform information here, it will compare and we're gonna know the coefficients. See yourself closer to 1 is better, right? So you don't try to go below 1 or above 1, you try to keep it into 1. I don't think give or take is fine, but you try to keep it between there, so you know that your calculation for the 3D simulation and this is accurate. Any platform data that have a really good coefficiency, when we enter the data into this, we know for a fact we have accurate data. So that was the major problem I had with all the platform have a deviation. I needed to solve that problem because who had the real data? That was a major problem. That's why it is a develops the software, right? And so we work with precise data, and we're getting the loss power, load power. Um, so and this is like the total loss power. So if you subtract this to this, right, and the total power here itself. So anyway, I didn't really punch in any valid information over here. I turned up things so things will not look pretty down here, right? All this information, how Tesla of we have here, right, 0.6, so 650 millitesla, right? So you know if we're going to burn it, the core material itself or not from the datasheet. We're looking at all these guys here, so it have really good information in this, right? So let's stop this, right? Boy, this will take a while to stop, right? Because when you have it running, it's have to offload from memory. You have an info here, and click here, you have like all the information, how to go about using this. I type that and all the features itself, right? So now this is the percentage we will be getting it from in this calculator here, straight down on the bottom, right, where we see the percentage. We put that in here, right? The image, the MOSFET will, this is a monitor from here. We have an image here, we have current per MOSFET. We look at the datasheet in the MOSFET. If one MOSFET, this exceeding or two less, you put more MOSFET, so you mash up the MOSFET, right? The total losses in the total MOSFET 160, that's all of these guys here, right? So we pretty much will mash up this MOSFET because the current overbearing for it. 8 MOSFET we use in a total. Um, Series current, which is like flowing through from here, from this bridge going across here, right, across the side, either side. One cycle current will flow in negative, current bring negative through here and go up to the positive side, right, vice versa. So the series is bridge MOSFET power loss, we have 640. So this will be MOSFET plus the core itself, the foil, and the other MOSFET itself. So all that will total up to this, right? Now this is an estimate itself. So before we run a lengthy hourly calculation, we do not want to, you know, waste time. So we could see if everything is fine here, and we make changes. We know the MOSFET is going to damage. We put like 3 MOSFET, and put 3 MOSFET, we will see the current will drop 150. We look at the MOSFET data sheet if we can handle that. We say no, let us put 4, right? And we come to 115. The MOSFETs can handle 150 or around the or 125 or something, and we say okay, we will use this. Let me see if I can find that data sheet. Right, so let us kind of like look at something here now. So the data sheet for the MOSFET, this is my document that I created here for my design an amplifier here. So it's a lot of documentation that has been going on, right? So it's lots of data, right, and equations. So anyway, what we're looking for here is a MOSFET that we use with a very low ohmage. This one is 1.9 milliohms. This not it. This one is 2 milliohms. That's not it. This one here is 0.7. That could be it, and that is probably it, right? So let us look for this MOSFET, right? And this is the actual MOSFET, that is MOSFET with 0.75 ohms, right? Yeah, this is the MOSFET we have here. So this MOSFET here that we are using is a SMD MOSFET, flat. So I will have to create you know, a means to put this MOSFET on heatsink. This is 60 volts, and this MOSFET is ultra low, 408 amps. So we could pretty much use 2 MOSFET, right? And we're using half of the current, right? So if we're using half of the current, 2 MOSFET will be fine, right? If I use one go work. Yeah, actually one go work, but that maxing out the current, and we have a voltage that will be developing across it, so the voltage may go up. So yeah, so if we have one MOSFET, if we run one MOSFET, what we have here, okay, single MOSFET, dissipation for a single MOSFET is 160 watts, right? Now the wattage here is 375 watts. Okay, we could probably use one MOSFET, right? So we could probably use one MOSFET. I think $4 for one MOSFET, right? So yeah, we could use one MOSFET because we less than half, right? So I depend on a calculator to do maths, so yeah, excuse me, or I'll be working with a lot of number, right? 180 and we had 160, so one MOSFET could work, right? So this MOSFET is ideal. So if we put two MOSFET from the efficiency that we say here, we have 68, we put two MOSFET, 36, no, this is wrong area, that is the ohmage here, right? If we put two MOSFET here, we'll get 83% efficiency. If we put three MOSFET, we get 88. If we put four MOSFET, we get 91. If we put five MOSFET, we get 92. So we kind of like looking at, so if we have to do that, right, if we have to put that kind of MOSFET in today, what really making the efficiency up is because we lowering the ohmage on it, right? Ohmage per MOSFET is 7.5, well, 750 micro ohms, right? And the current going across is, if you use a lower MOSFET to match this, say a 150 amps MOSFET, a cheaper MOSFET itself, and that MOSFET could be 1 point something watts, so we could use a really low power MOSFET at a lower price and use that. But the thing about it, we may not find a lower power MOSFET at that kind of ohmage, right? And the only reason why it is ohmage is like this, so we have to test other MOSFET and see. So when you're looking at pricing, what I feel I would do, I will create a little maths area here, enter the prices of a few MOSFETs. Yeah, I could do that. Enter US prices of a couple MOSFET for the part number itself, and while sending this up, we pretty much could see which one making a better price, so you can make a determination based on the efficiency on this, right? So because the total MOSFET that we'll be using is 20 MOSFETs, right? So you say 6, where will be at 24 MOSFET, efficiency going up there. If we use 10, well, be careful, capacitance efficiency going up to 95. So let us just use 5 MOSFET, we at least over 90%, which is fine, right? So yeah, you had decisions to make over here, so I will have to put these in these boxes over here to help make that decision, right? And the voltage that went into this was 18 volt DC battery, and the calculation that we need for the low pass filter is 35 volts capacitor, right? So minimum 35 volts capacitor, not even 25 volts, 35 volts or 18 volts, right? And the capacitance have to be, this is 10,000 microfarad, yeah, more likely 10,000 microfarad, right? I will have to change this format and do this format to be millifarad. I feel put this as millifarad, and let's change this to millifarad, right? So when we start to cross some big numbers, we will kind of keep it there. I'll put a button here for milli to micro or something like that, and let's update this. Yeah, so all those fine things I could pretty much do if we want to look at certain values. Yeah. So that's that. This is the allowable voltage ripple. I'll put this as an indicator here. I can't remember if this was calculated or if this is to determine for calculation, but I think this is what calculation maintained here as ripple, because the type of stability and ohmage I run in here, it kinda like do fine. So now we have the non-3D inductor, which is not a physical inductor like the inductor say would assimilate. This is calculated by the frequency and certain parameters. So we have like the impedance is zero point 0.6 ohms, um, and lots of the energy go be across over here. So this zero point 0.6 ohm go have some energy across here, and not much going into the much going into the transformer, but we could see we have some losses here because this is 600 micro ohms, right, which could be greater than what we have here as a MOSFET. Yeah, so the MOSFET have no kind of power, but so many power coming here. I need to do the inductor of this, but unfortunately I was unable to compute that, I believe. Here I did it here, right? Think of a DC ohmage here per layer, so we gain like these guys here, right? And so yeah, I was able to do it in these guys here, right? So I didn't went through the hustle for that over here, because in 3D now we're gonna be more accurate in 3D, right? So yeah, to work out that thing there, I say, you know what, I'm not going to be doing that. I don't work out there, have an average, and you know. So yeah, so we had inductance here, right? So what I'm going to do, I'm going to minimize this. I'm going to throw this here, throw this up about here, throw this about here, and let us run simulation, right? And run this simulation. So this simulation going to be running here now. I will pause the mic this to show the simulation running, and I will just monitor it. I may pause and then open it back when it comes close to finish, because it is going to be going back and forth, but I will just leave some of the animation to do for a while till it cross there's 210 microseconds. A duty cycles around 20 microseconds and a period of about 10 microseconds. So I think I may leave it to run to 30 microseconds before I pause it. So at least a cycle and a little more, you will see those information, how it goes, right? So what I would do, I will just kind of hide that there, right? And let's kind of put this to the corner here, right? So we kind of like want to have this. I feel like we'll just turn off the light on this, right? I'll turn off the light on this, so at least we get to see the real color. So I'm going to cancel here. I'm doing a test as well, so I want to see it could pretty much resume back. I just want to double click, send this up, and just come down here and then run it back here again, right? So at least we get more space, right? So the cancellation and resuming work, they didn't crash, so I just wanted to see that. Now when the simulation taking place, right, you notice that when we actually build, we get a circle when we build, because we determine that itself. We kind of like seeing that not happen over here and these guys, right, which is fine, because as soon as the background information compute itself, it will update this and you will see the curvature happening here and any simulation. I have to do a message box to show certain details. I make an attempt to do it. I was seeing some problem with it. I pause it and I compile, and I here I still we just run this thing, test it, before going to another phase, right? I had one or two hiccups with these things, but now some big progress here, and we're just going to look at it. Okay, by the time that trying to come out of the is setting up equations in the background, let us look at something here. We have 18 volts, we have I think 14 layers, right? 14 layers, one turn, right? And I am parallel, and I see primary side. So, well, I think it was a 900 amps or something going in today, right? And that 900 amps are going in today, we have 18 volts. Okay, look, so this is it here. So we have this going to be running, right? So zero time here. So yeah, so we have that current that going into it, 18 volts. But if we say we have the same secondary, we got 18 volts coming out. But instead of that, we have 3 layers to double up the current, and we have 5 turns. So 5 turns by 18, we can have little drops, but we just using a raw factor here. We have 90 volts, right? So that is our transformer by ratio. So if we have 90 volts across a 1 ohms, right, we're looking at power. So we have voltage, which is 90 volts by 1 ohms, 8100 watts, right? So we're supposed to have an estimate 8100 watts and pretty much less, because we had to consider core loss, primary and secondary foil losses. We have inductor, which is um, a non-dimensional inductor, and capacitor in the circuit that will have losses. Then we have MOSFET that will have losses. So we have losses that will drop this down itself. Okay, so we will be looking out for something less than that. We're not supposed to get anything above that unless the ohmage is less, I don't know, restrainer. Now, more load that we put, the magnetics in the core might damage, right? I saw that in third core transformer and amplifier for class D in the output filter side. Um, Calculation was an issue, right? So as you can see over here, right, we have high current density here, magnetic flux density here, and low over here, right? So let me just put this in the correct orientation. The default in the wrong direction, I will have to fix that. This is the correct direction, X up. The primary foil is this one, and secondary foil is this one here. And what we're looking at here now is we kind of like looking at scene. I wonder if we have any transparency, right? So we have the transparency here, right? So when we're looking at the current density here in the foil, we can see it kind of like come out. So I'm going inside here, same thing over here, right? The thing with this is because we have like all the primary here and all the secondary here, but if we do it like primary, secondary, primary, secondary, primary, secondary, primary, secondary, they go up, right? The magnetic field that is being coupled between these guys does not penetrate the entirety of the rest of the foils. So they take more heat will happen in the between here, and because of that now we can have instability, right? Now even though we get any energy and stuff and thing, you're looking at futuristic issues itself. So this will work, but one of my best advice is that building transformers, they put negative here negative primary secondary, so the magnetic field from a primary foil will be able to couple next to the secondary, and next primary next to secondary, and back forth, right? Now I pretty much will have to do a version of that, right? And once I get all this right, pretty much a version of that is basically a button to configure. When I say a button to configure, I got to pretty much do some physics and the geometry and put a button and write my code for that, where we can pretty much kind of distribute that properly, right? It is a lot more work, but I didn't want to disturb it and make a temp on it, but it's like a lot more work, and I say, you know what, let me leave this, let me do this here. I know that exists, and so all those things for the mechanical engineering, I could pretty much look at, you know, building the transformer final stage like this or like the other configuration. Now when I'm doing that, I see in the simulation results I will have to manufacture the two configuration and do real-time bench tests. And those real-time bench tests now, I will have to use infrared cameras, and I will have to put sensors in certain, like inside the transformer itself, put sensors itself to be able to measure the temperature. So in other words, now I write in another software, right? And the other software will be written with um, acquisition controller to measure the actual temperature in locations inside the transformer core itself. Um, and I will write a software itself 3D, and we will look at the temperature. So in real time, I will be able to see the temperature, the magnetic flux, all these things. I will be able to measure itself. So I would like to see those things. Um, so yeah, I will have to do those things. So that's a whole thing by itself. We're at 4.2 microseconds. So I will leave this for you guys to kind of view, right? And I will not make noise. Okay, so the simulation is now finishing. So if finalizing here, I will run simulation for the loss. This shouldn't take that long. So we can see the new loss itself. We can see these values popping in over here. Right, so we have like 4.6 watts is 4.9 watts, close to 5 watts is 5.5 watts per MOSFET, right? Let us do the loss at one time, and we could also see 7636 watts is across the 1 ohms load. So we have some good ratings so far for what we look at, between 7 to 8,000, so that is really good. So our estimate, the 3D was able to give you the precision, right? And when it comes to all MOSFET, is a 57.58 watts in heat. So let us look at the simulation, not this one. Right, so I will have to, this is calculate, this is what we punch in here to be able to get a certain value, but this is what this compute, what I will have to get. I will have to get a power going in and power coming out, and do a data table for that, and have that somewhere wrong so we have comparison. And when the simulation finish, we will get a comparison, to have a look at, right? Because we did not put no high set of mesh for many calculation, the data itself will come in like blockish, because we're not going long in precision. This is just a simulator. Take a couple of hours, well, about an hour or more, right, close to 2 hours to take to simulate. I just had lots of well, actually I'm not sure, but probably an hour or two. But when we look at the start of the video to the end of the video, we can see the time frame down here, so we can know exactly how long it took. So we're waiting for this heat signature here to show. So I will leave it here for the time being and let it work on that. Okay, so we now see the update here. So let us browse through some data. Right, so the main graphics, I not seen where that actually hidden away, but I will have to look back at my codes. Oh, actually no, it's not hidden anyway. Yeah. So main graphics, where that is. Oh, main graphics, look at here. Right, so let us pin this. Let us drop this guy here. Now, main graphics itself window is where we could actually, browse through anyone in configuration to look at it. These rest of the guys is fixed. We have a DC resistance with scaling will be very small into pico ohms. So we have like the secondary is 161 pico ohms, and 34 pico ohms is the primary, which since is like 14 layers, one turn, it'd be very low. And since this is 3 layer by 5 turns, so this is why it is the ohmage, DC ohmage, and this is high. Then we could go to the voltage across all the components. Well, not really all the components, but mainly, you know, well, actually all, I believe. So we can see this now. Okay, so we had a battery which is like this red guy here, 18 volts, and the primary which is, 17. Okay, I keep on touching battery. So 70.6, right? Which this is pretty much, if you calculate the other components and you check the balance voltage, you'll see exact thing. So the losses is like 0.3 volts in loss, right? So we're seeing the primary voltage coming in here. Well, the transformer for square wave itself, but sine wave easier to simulate itself. The square wave is, lots of load. So anyway, computational load, I mean, right? So we have like the inductor here, in small scale. So if we see the inductor and the MOSFET voltage, they pretty much close to the transformer voltage. We know that we're going to have lots of losses, so it kind of have a scale factor here. So we could pretty much watch this, this eyeball it and realize, okay, this look good. And then we have the secondary voltage. Since we have like 5 turns and 5 turns by 18 volts, since the 18 volts is coming in, is like 90 volts, so we have 85 volts. So that is fine, because we can have the primary and secondary foil and losses, the inductor and losses, the core and losses. So those voltages will drop, coupling, and you get a little below 90 volts. So this is what we have here, 85 volts, which is fair enough, right? Hence the reason why it is we end up with 7600. We could be about 8000 volts if we have no kind of losses. Yeah, we would be fine, right? So that is fine. Let us look at the MOSFET. we had a MOSFET over here, but I just pulling it up in the main windows here. Main windows is to browse through all. So the maximum power loss and heat is 57 watts. So this basically meaning your heatsink could be very small. You know, you don't have to worry about much heat and fan and fins. You know, you really could go compact according. So this is really low losses in heat. That's all the MOSFET. And when we look at a pair of MOSFET, right, we have like 27 watts. When we look at a single MOSFET, is 5.69 watts, which is really good, right? The resistive load is what we was looking. This is how much going across the speaker itself, right? And this is just one planar transformer, actually one planar transformer, right? The theoretical transformers of them, there's in car amplifiers, is like 3000 watts peak, and there's really try to extract half that, so it would not have instability and spikes which could damage the FETs, and you know, so it wouldn't go try to quarter saturation itself, right? Now we check on this and we have to check the flux density. Now the entire thing will have a maximum peak of, you know, flux density. It will have some spikes itself and like little corners here, which is really minor, right? So you know, we have an estimate for that and this histogram, but it's not working at here at the time because I need to fix that, which is not a problem. It's just that it's minor. The major things was fixed, and this is the last thing I'll go fix, right? So let us look at the inductor power loss, right? This is the non-dimensional inductor. So this is a non-dimensional inductor here. So we have 272 watts peak. Now we're not a flat wattage coming across here. If you notice, we just have it like oscillation, right? So we have some spike, but yeah, pretty much if we had to compute this, we probably might end up around 75 or 50 watts or something like that. That was 75, 50 watts. We're gonna end up in losses, which is okay. So that's that. I didn't bother to show the capacitor because the capacitor power and current rating kind of pretty much it parallel with the inductor according to the topology that I use. So both of them will have like the same in that sense. So you know, once you see this, I know the capacitor going through. I will put a note for that, I guess, but say what? Inductor, primary, secondary current. So now we can see a high current in the primary side and a low current in the secondary side. Well, the ratio will be different, right? So the primary is 435 amps, right? And that is right peak. So peak to peak will be 960 something amps. So let us look at some of the information, which will be this and this one here, right? So we just close this guy out, close this one out, close this one out, and we look at what we have here. So we have 924 amps, right? We have 435, so 435 by 2 is 870, and we have 924 amps, right? So 435, yeah, 435. So you can see the estimate that it actually close, right? And what the wattage was per MOSFET, right? Close to 5 watts, right? And the single MOSFET have 1.2 watts over here. We use 5 MOSFET. We use 5 MOSFET in the MOSFET group, right? So let's give we that. We see about 5 here, and yeah, so that will be okay there. Since we doing peak and peak to peak, 1.2 by 1.114. Okay, that is that. So anyway, total watts we say 50 something watts, and all MOSFET showing 25, right? So pretty much all together by twice is 55. So yeah, peak and peak to peak, right? So kinda back and forth there. So the wattage that we have 8,000 watts, we have 75, and what we have over here was no 75, right? So we kinda pretty much matching up there. Efficiency that, but I have to do this efficiency. I got to do a calculation for this efficiency with the waveform itself. When I do that, I will have to write a code. Now, actually, I could do that in a table, so that is fine. So, histogram not going to show, right? Histogram. I had to put some option for the histogram where you can actually punch in from whatever millitelsar to 1 millitelsar. So you want to pretty much evaluate within ranges, so we can see exactly how much percentage per range of millitelsar. If we have from 10 millitelsar to 20 millitelsar, 10 difference of 10 bandwidth of 10 millitelsar, and we say from 20 millitelsar to 30 or 40 millitelsar, we know how much percentage we have in a transformer in that. So we know if we have the core only doing like 400 millitelsar, and we have like probably about 25% millitelsar, 25% of 400 millitelsar, that is fine. That is really good, right? So once it does not cross 50% over, where we kind of saturating the core so ever often. So you can have one or two little small spikes, but not a high percentage. So the model when I built it, that working here, but for some reason it didn't come across here, so I got to fix that code, which is not a problem, right? And then we had a BH curve. Now I'm not using BH curve on the data sheet because it take more computational power for no big difference, right, in results. So I'm using the permeability. So I'm using the core material permeability to do calculations, so it will be in a straight line and not the BH curve you see, because you have to take the manufacturer BH curve, which you have to use a digitizer, which is not a problem, to get that data out and put it into this. But the resources and time and computation just to have a little difference in results make no sense. So so this could work pretty much fine. And so we have a maximum milliters of 361, right? So that's that. I may have to correct this. I have to verify this back itself. I think if I did this per foil, probably per foil I did this. I didn't think I did for each layer, and I think I do this from one layer, so you can see 50 amps or something like that here. But I will pretty much do that, put proper results with all those things and notes itself, so at least when I'm reading it, it makes sense. So I'm going to close out this guy, this guy, this guy, right? And on the close of this guy, we're going to do some measurement. Not here, not here, but here. Right, so when we're looking at the we have three graphics, right? So we have graphic 1 for this, graphic 2 for this, graphic 3 for that, right? I would label these. Okay, it label here, right? Cross section, surface, cross section, and losses. So I could just remove these graphics 1, 2, and 3. That kind of confusing, right? So if we click this time over here, we actually can see results. So we have 15 millitesla because we scale millitesla, and the core, this top core here in the positive z axis is this one here, and this one here is the minus z axis. So we have the z positive axis is this one, negative z axis core is this one, and the secondary is the bottom one here. Another secondary, the primary, sorry, is the bottom foils here, which is this guy here, and this top one here, scale here, is the secondary, the top side, right? I may have to put some form of indicator. I will put a form of indicator like a screenshot of this and a small pit here underneath here and show the orientation and labels properly, so when you look at this you know what is what and what you're looking at. So because when you're clicking all over the value itself, if we look at over here we have green, so we have like 1.6 probably by the green, and we just go by green here, right? So if we if we had the light on, it will give you different kind of coloration, right? So turn the light on, I mean off, so it'll remain the same. So if we pretty much, you could come move this across here and see where green match up itself, right? And click, you see 16, right? So we have 16 right by the green here. So from 15 to 16 here, so the green match up here, we have 16, right? Now if you look at the bottom here and we look at this core, which is this one here, if we look for green looking the same as this, it wouldn't match up the same, right? So let me find, right, so there's a close green over here, right? This green about here, so you look at this right here, we have, right, we say this, okay, this is green. What we're gonna have here, 34. Now actually what we get, 34, so we've seen 34, and 34. "28" is blue. Okay, more likely might be this one over here. Okay, I see. Yeah, because 33 is around here, so this core is this one and this south core here is this one, so more likely I